Hi everyone, this is Stefana Muller. I'm the product manager for CA Service Virtualization. And today I'm going to be sharing with you Opaque Data Processing. We're going to first go through a few slides on what Opaque Data Processing is and how you can use it, and then I'm going to go into a demonstration. So to start out, I like to use this quote here by author C. Clarke. And he says, any sufficiently advanced technology is indistinguishable from magic. And when we first presented this technology to our team, even in engineering, after it was innovated on in our labs, they said, how is that happening? It seems magic. So it's kind of funny that this can apply here. I'm going to actually try to, during this session, show you how this technology really isn't magic and it's real, and we can put some real hard facts around how we create this environment for for processing opaque data or data that we do not understand or know. So what this is in a nutshell, I'll kind of give a high-level overview of opaque data processing. What opaque data processing does is it allows you to virtualize or create a virtual service without requiring any knowledge or decoding of the protocol that we're reading, right? So when you're creating a virtual service, you're recording transactions back and forth across the wire. Opaque data processing can actually record and track those transactions and be able to learn them well enough and match a request to an appropriate response without having to translate that protocol or know where the operation, the argument, and the data resides in that message. So some of the cool things about this is that this technology is applying a genome sequencing alignment algorithm, and it helps us find patterns within a message to be able to match up the request that came in with a request we've seen before. And the great thing about it is because we're using this algorithm and we're not trying to translate the technology or the protocol, we actually can virtualize a much wider range of protocols without having to know the language, if you would. So, in addition to this, we found through many tests that ODP is extremely accurate. The accuracy is a high rate of over 99.6% on average. The majority of protocols we've tested this against, even ones we did not know and weren't given information on until after, we found that there was 100% accuracy. Okay. So just to kind of frame the problem in case I lost you on the last slide, what is the problem that we resolve with service virtualization, and why do we need opaque data processing? So the big problem with service virtualization is, or that we're trying to solve with service virtualization, is that we have constraints in our development cycle. A developer who's developing the front-end app here at the top may need assistance from a system in the back end. He or she may need to hit that system and get a response from that system. But unfortunately, as we know, the mainframe in that back end system is not available. Your database is not available. Your cloud service is not available when you're in development. So what we do, as you can see here, is we virtualize away those constraints, and we create what I like to call smart stubs that will respond to your front-end application with a complete message that will allow your front-end application development to continue. So like I said, we are going to go through some of the background here. This is how service virtualization works in a nutshell. There's a lot of context here, but I'll try to sum it up. You capture your transactions, whether you're capturing it by recording it, by getting it from log files or whatnot, but you need to get a set of transactions which have a request and a response so that we can figure out what that looks like. Then in the process step, which is the second step, we actually go through a process of figuring out what this data is, finding the operation, finding the arguments, figuring out what things we can do with that data so that we can respond properly back as a virtual service. And last but not least, we create that virtual service. So the challenge you can imagine in this process is that you can capture as much data as you can, and model, you could probably model almost anything once you have that data and you translate it. The bigger challenge is that process step. I like to call this the DPH challenge. We call this the data protocol handler. And individuals on our team and individuals within many of our customers actually take the time to write a data protocol handler. So, for example, if you were to use REST, and REST wasn't supported in the past, we actually wrote a data protocol handler to figure out the REST protocol and know where an argument lies, where to split up the message so that we can appropriately identify the specific information and respond appropriately to that information. So, like I said, the DPH challenge is a challenge, though it makes our software very unique, right? You can, you have an understanding of your protocol, you can definitely pretty much act exactly like a live system would if you understand that protocol quite well. However, if you don't know the protocol, what if it's a proprietary protocol or the subject matter expert that you worked with is no longer available? They left the company, or they, might not have remembered the information because they built it so long ago. What if the protocol is new or nobody is a subject matter expert within your company? What if you have a copybook and it's just incomplete or incorrect? I can imagine that happening quite often. So as you could see here, there's a few different ways the DPH doesn't work. If you don't have that expert and you don't understand the protocol, a DPH is very difficult to create. And unless you can identify the operation body and syntax of a message, you're really not going to be able to respond to it correctly. In addition to that, it takes time. Even if you do have an expert on board, it may take a few months for a DPH to be created, and especially with some advanced protocols like Swift. We actually at CA had to find an expert to bring on the Swift support. We have that today, and the cool thing about it is we were actually able to test it with ODP, which I'll share with you in a moment. So, like I said before, when I was giving the high-level overview, ODP Essentials, what it brings to you, what it allows you to do, it virtualizes services without requiring any of that knowledge or decoding of the DPH. So you don't need a DPH, you don't need that human to read the data. In addition to that, it takes a look at the data and does this genome sequencing alignment to figure out the byte level patterns within your message. And that pattern matching is exactly what allows us to respond. So instead of responding by translating, we're actually doing these byte level pattern matching. So if we're getting binary data in, we can actually respond to it in the correct binary data back. That's really key, especially when you're talking about human readable. We all know that binary data is not that human readable. Okay. So I actually want to skip through a bit and take a look at the ODP approach. We just talked this through. I'll walk through really quickly. The current approach is that the client sends a request in to the VSC. The VSC does a quick decoding. It does a match, and it sends a response back. In opaque data processing, we actually skip the entire step of decoding. And what happens is there's this matching algorithm that runs live. And as you feed more data into opaque data processing, it gets smarter. So the more understanding of a message structure it can have through that algorithm, the more it can understand where your operation is, what syntax looks like, where your arguments are. So I give another example here of what it kind of looks like. So I receive an incoming request from the client. That's my first line. The green and red boxes here. The incoming request apply, and then I apply a. I receive my incoming request, and then I try to find within my library of requests that I had prior, I try to find a matching request. And the way I do that is I take each byte and I line them up. And within each byte, I try to find a few things. Try to find what's different, and I highlight those differences, and what's the same. As you can see here, the term get user seems the same. In my ODP approach, this actually will say, hey, get user seems to be a more similar thing. I've seen it multiple times, and therefore I might say that is more important to look at. This is what we call entropy weighting. We actually weigh what things are different and throw those as down as less important to match on. So that allows us to make a more accurate match. Once we do the incoming request, matching the request within the image that we have or the library that we have, we send the response. And the cool thing about sending the response is that we can actually use information from the incoming request to send that response. So for instance, if I said get user Sam, it won't respond it won't respond here's user Stefana. Instead, it will use the incoming request data that said get user Sam and respond with that. It can actually identify what we call that magic string. Okay, I mentioned entropy weighting. Here's a quick slide on it. It increases the accuracy of our matching. You can actually figure out what things within the byte pattern are changing more often. Again, entropy weighting gets more and more accurate the more data you throw in. A question often comes up, how much data do I need to get ODP to work? And the answer really is at least 2 of each operation would be necessary, and that would make ODP know that that was a common item. For instance, if the operation was add user, you'd want at least 2 samples of add user request and response. That would allow ODP to identify add user as a common item. Again, if you have more samples, that will make it more accurate. Okay, I just gave a sample of how ODP approach with regular ODP approach with matching and the entropy weighting happens within the process. So as you can see here, while I'm applying the algorithm, I'm also applying the entropy weighting. So that happens at the same time, which actually quickens the response from the algorithm. And here's a bit of accuracy stats. As you can see, accuracy goes up significantly when we applied the entropy weights. On IMS, we tested it out. Initially, we were getting only 77% correctness, and then when we applied entropy weighting, it went up to 100%, and that's just amazing. I'd like to point out also with Twitter, the REST protocol that we did a test with. Initially, we tested, and it's not on the screen here, but we tested against our own data protocol handler. Remember that constraint of the data protocol handler that I talked about earlier? We initially tested with the data protocol handler, and the data protocol handler was not as accurate as ODP. So we actually learned from ODP. We were able to learn what we were doing wrong. Because remember, the data protocol handler is built by a human, and humans do make mistakes. Okay. One thing that often comes up, everyone always asks me, is when should I use ODP? And ODP, like I said, provides that turnkey solution to virtualize something, or a protocol rather, that you do not support today. Rather, whether CA doesn't support it today with our service virtualization, or it's something that nobody understands or nobody even knows what the protocol is, ODP can really help with that. You do need some reasonable data. in the ODP library in order to make it smart enough to be able to match and respond correctly. Like I said, at least 2 of each operation. Obviously, more is better. You don't have the ability with ODP to force specific behaviors. So just remember, it's using an algorithm and byte level alignment. It's not going to allow you to do things like edit that alignment or edit the response. It's in the DPH model, you can do that very easily. You can create, negative tests or so on. But in this model, you cannot. So remember, that's a restriction there. In addition to that, we must, if you have an encrypted message, we can't decrypt it in ODP. ODP is doing a byte level alignment, and encrypted messages are hiding those bytes, so that's not going to work. And the other thing to keep in mind is that ODP is not going to manage state. So this is only for stateless transactions. I wanted to mention this before I go into the demo and thank the team that put this together. Miss Miao Du received her PhD on this technology. That's one of the coolest things I've seen in my career here. It's one of the greatest technologies I've seen, applying genome sequencing to data protocol handling, completely spanning 2 different industries. So hats off to Miss Miao Du. She was a PhD candidate when she started this research, and I believe she received her PhD recently. The other team members include her professors, our lead in the CA lab, Steve Versteeg, our lead software engineer, Robert Williams, and our lead product manager, Chris Kraus. So thank you to that team for putting this all together, not only doing the research to figure out how to remove the constraint of the DPH, but also productizing it so quickly. Okay, now we're going to go into the demo.